So for problem number 1, it wants us to draw the photoelectron spectra for 3 elements, X, Y, and Z. Okay. So the first thing we have to do is determine what X, Y, and Z are. So if we go through and do that, we see that this is 1s2, 2s2, 2p, and that is twice as big, so that's going to be 2p4. So we know that this is oxygen. We know that this is going to form a compound, so it's either helium or hydrogen, and we know that it can't be helium because helium does not form compounds, it's a noble gas. So this has got to be hydrogen. And element Z, 1s2, 2s2, 2p2. So we know that's carbon. Just as an aside, I want you to notice that this is the high side and this is the low side, just based on these numbers. So we know that the 1s2 should be closer to the high side because according to Coulomb's law, it's closer to the nucleus. Note, once in a while, this might be the high side. I always look for that 1s2 peak. Okay, provide the Lewis structure, molecular geometry, and polarity for the compound YX. So here's Y. We know that that's H. And here's X. We know. Oh, I'm sorry. This is 1s2, 2s2. So that's 2. That's going to be 2. So this is going to be 2b5. So we know that that's F. Okay, sorry about that. So that's F. Okay. So octet, that's what it wants, minus valence, has, divided by 2. So what does it want? Well, it wants to have 2 plus 8. That's 10. We know that there's an exception there. Hydrogen only needs 2. Minus what it has. Well, that's 1 and 7. So that is going to be 8 divided by 2. So that's going to be 2 over 2, or 1 bond. So we're going to draw the Lewis structure for that. It's going to be HF. And we're going to put our lone pairs around F. Okay. And the electrons are pulled closer to F because F is more to the right on the periodic table. And in terms of its molecular geometry, that's going to be linear. Okay, so that's that molecule there. Provide the Lewis structure, molecular geometry, and polarity for ZY4. So Z is carbon and Y is hydrogen. So we know that that's going to be CH4. Okay, wants minus has divided by 2. So we know that what it wants here, there's 8 here, and that's going to be 2 times 4 is 8. So that's going to be 16 minus has. Okay, so we know that here, that's the valence. So carbon has only 4, and then there's 4 hydrogens, each having 1. That's going to be 8 divided by 2, 4. So now we're going to have C, H, 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 H. There's going to be no partial dipoles because we know that with the carbon-hydrogen bond, we don't count that. And the shape of this is going to be tetrahedral. So then it says, when 0.4 grams of the more ideal gas, YX or ZY4, are contained in a rigid 250 milliliter container, what is the pressure? So first off, we know if the temperature is 35 degrees Celsius. We know we're going to use PV equals NRTE. And the more ideal gas in this case is going to be the methane. It's nonpolar, and according to kinetic molecular theory, nonpolar gases have only intermolecular forces that are London dispersion. This is polar. This dipole does not cancel out, so it's going to exhibit dipole-dipole forces. So we know we're going to be dealing with that, and what we're going to be solving for here is the pressure, so P equals nRT over V. So let's go ahead and do that. We're going to solve for the moles. We know that that's 0.0821. We know that this is going to be 273 plus 35. Okay, that's going to be 308 Kelvin. divided by the volume. 250 milliliters divided by 1,000 is 0.250 liters. Now let's go ahead and do this mole conversion real quick. We know that we're dealing with methane gas, CH4, so that's 16 grams in every 1 mole is equal to 0.40 grams divided by X moles. And that is going to be our N value. So let's go ahead and solve that. We're just going to simply take 0.4, we're going to cross multiply, and we're going to take 0.4 and we're going to divide that by 16, and we're going to get 0.025. And then we're going to multiply that by 0.0821, and then we're going to multiply that by 308, get an answer. We're going to divide that by 0.250, and we're left with 2.5, and it's going to come out in atmospheres. Next problem, same kind of deal here. So they want us to provide the Lewis structure polarity for AB3. So let's look here. 1s2, again, this is the high side. 2s2, 2p6, 3s2, 3p3. So we know that's going to be phosphorus. And again, it's going to form a compound. So we know that that's got to be hydrogen. So we have PH3. Okay. So wants minus has divided by 2. So wants, this is going to be 8 plus 2 times 3 is 6, 14 minus has. So we know that phosphorus is 5 plus hydrogen, which is 3, divided by 2. So that's 14 minus 8, 6, divided by 2 is 3. So it's going to be PH3. And we know in this case that the phosphorus is pulling harder, so that's plus, 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 and this is a pyramidal structure. Now, do you predict AB3 to be more soluble or mix better with H2O or CO2? Explain. So we know that's going to be H2O, and the answer is H2O and PH3 are both polar molecules and will interact via dipole IMFs. So let's go ahead and show that interaction diagram. We know that the water molecule looks like this. Obviously, you can do want minus has there. And we know in the PH3 molecule, P pulls harder on those electrons than H. It's more to the right. That's our rule when it comes to simple intermolecular force diagrams. So we could draw it like this. Not the best drawing. I'd probably keep those H's further from each other. And there's your dip-dip IMF. Okay, and that explains the solubility. They'll mix with each other. All right. 3. The photoelectron spectra for 2 atoms are shown below. Let's go ahead and do this again. 1s2, 2s2, 2p6, 3s2, 3p1. So we know that that's going to be aluminum. And this one threw you off a little bit here. And this one, this is the high side. Okay, I just wanted to keep you on your toes. 2s2. And this is going to be 2p3. It's a little bit higher than 2p2. We see that that's 1, that's 2, and there's an extra 1. That's 3, so that's going to be nitrogen. So it says element C, which we know is Al, reacts with element D in this form, D2, to form element C3D2. So Al3 D2. And I actually messed this up. It should be C2D3. Al2D3. So it wants us to go ahead and balance this reaction. And I actually don't like the way that I did this here. This should be, I'm sorry. Apologize. This should just be, I'm just going to start over here. Sorry. Element C, Al, reacts with element D2 to produce, which is N. Jeez, the freaking Louise. Let me delete all this. So annoying. I'm sorry. Me too. Oh, me too. I'm so sorry. Okay, that was annoying. So element C, which is Al, reacts with element D2. D is N, N2, to produce CD, which would be AlN. Okay, and I'm going to balance it now. Okay, so when I balance it, I'm going to put a 2 here, and a 1 there. Super easy. My bad on that. Okay, so we do a little stoichiometry. If 0.5 grams of element C, which we know is Al, reacts with 0.50 liters of element D2, which we know is N2, what massive product is produced? So let's first go write our reaction and do our BCA table here. Ooh, we already did that. I know that that's a 1. B, C, A. Boop. Boop. Okay, so we got to do some conversions here first. So let's do the AL. 27 grams per every 1 mole, 0.50 grams per every x moles. So the first thing we're going to do is divide 0.5 divided by 27, and that's going to be equal to 0.0185. 0.0185. So that's going to be 0.0185 moles. And 0.5 liters of N2, well, we're going to have to use PV equals nRT here. So N equals PV divided by RT. And I told you that the pressure is 1. I told you that the volume is 0.5. R is 0.0821. And the temperature here is 25, so 298. Okay. So 1 times 0.5 equals that, divided by 0.0821 equals that, divided by 25. So 0.24 moles. Okay, so you need 2 times as much Al, but you don't have anywhere near 2 times as much. So you're going to run out of that first, 0.0185. So that's 0 moles. Okay. Here it's going to be 0.24 minus 0.0185 multiplied by 1 over 2. Okay, so okay, so it's going to be 0.23. This is going to be 0 moles. So 0 plus 0.0185 multiplied by 2 over 2. So it's going to be 0.0185 moles of AlN. And the question said what mass of that's produced. Okay, so now all we have to do is convert that to grams. So the molar mass of AlN is going to be 27 plus 14. Okay, so that should be 41. So we have 41 grams per every 1 mole is equal to x grams per every 0.0185 moles. So that times 0.0185 equals 0.75. right, number 4. The inflation of a car airbag. Okay, so now we've looked at that in class. We have the car airbag here producing a bunch of nitrogen gas. And the standard airbag contains 20 grams of sodium azide. We know that that's a solid in there. And it wants to know what is the volume of that in liters of nitrogen gas that will fill the bag. So the thing about this one, we need to balance this first. So let's go ahead and rewrite NaN3 plus Fe2O3. And I wanted to give you one doozy to balance. Na2O plus Fe plus N2. And then this is going to be B, C, A. So in this one, I've stared at it for a little bit, but I think the easiest way is to start with the O's. 3 there, going to put a 3 there. That gives you 6 NAs, so I'm going to put a 6 here. And that gives us 18 N's, so I'm going to put a 9 there and a 2 there, and I think I should be balanced. 6 NAs, 6 NAs. 18 N's, 18 N's. 2 FEs, 2 FEs. 3 O's, 3 O's. So good to go there. So let's go through and let's do this problem. So they say you have 20 grams of NaN3. Okay. And it says assume excess Fe2O3. So you have excess here. So you know you're going to end up with excess here. Let's go ahead and convert this to moles though. So Na, so N3, that's going to be 14 times 3, plus Na, which is going to be 23. So there's 65 grams for every 1 mole, and that is equal to 20 grams per every X moles. So 20 divided by 65 is going to give me 0.30 moles. So we know this is the reference because they said that was excess. So 0.30 minus 0.30, 0 moles. Excess minus 0.30 multiplied by 1 over 6. This isn't the same excess as that, it's actually less. Okay. Here, we know that this is 0 moles, this is 0 moles, and this is 0 moles. We're going to go fill out the whole table just for the heck of it, even though they're only going to ask for N2 at the end. So this is going to be 0 plus 0.30 multiplied by 3 over 6. So this is going to be 0.15 moles. This is going to be 0 plus 0.30 multiplied by 2 over 6. So this is going to be 0.10 moles. And this is going to be 0 plus 0.30 multiplied by 9 over 6. So that's the same thing as multiplying that by 3 over 2. So, because 2 can go 6 2 times, and 3 times. So 0.3 times 3 divided by 2 equals 0.45. Moles. Okay, so then it says, what volume in liters of nitrogen gas? So 0.545 moles, we're going to have to use PV equals nRT here. V equals nRT over P, which equals 0.45 moles, which we found, 0.0821. T, 21, so 273 plus 21 is 294, divided by the pressure, which they said was 0.90. So 0.45 times 0.0821 equals that, times 294 equals that, divided by 0.9 equals 12.1. And that makes a lot of sense. That bag is around 6 soda bottles big. Okay. Do you predict the pressure inside the airbag to be higher or lower if the temperature inside the airbag is increased to 30 degrees Celsius? So higher. Okay. According to KMT, according to KMT, gases are more ideal if they expand. Gases expand better at higher temperatures. If V is constant, P will increase as T increases. Okay, so as those gas particles gain more kinetic energy, the pressure against the walls of the container will increase. Okay, clearly explain why nitrogen gas is appropriate for use in car airbags. So just nitrogen alone, okay, well, what does it want? It wants 8 times 2 is 16. What does it have? It has 10 divided by 2. So that's going to be 6 divided by 2. That's 3. Okay, we're going to look at this. So we know that it's linear and it's nonpolar. Okay, so according to the kinetic molecular theory, according to KMT, gases that are nonpolar and small, this is actually really small, it's only got 2 energy levels, small, are more ideal because they have only London dispersion IMFs and thus expand better. So azide, we got this azide thing, this N3 deal right here, kind of this weird deal in this molecule, and it wants us to talk about that a little bit. So provide the Lewis structure for N3. All right, let's go ahead and do that. So what does it want? Well, it wants 8 times 3. It's going to be 24. What does it have? It has 5 times 3, which is 15 plus 1 is 16, divided by 2. So 24 minus 16, well, that's going to be 8 divided by 2 is 4 bonds. So we know here we're going to have N, boom, 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 minus 1. Okay, the molecular geometry for this dude here is going to be linear. Okay, but it's an ion. So in the box below, draw and label a diagram that shows what would occur if it were mixed with water. So who's it going to go to? It's going to go right here. And bond right there. And we're going to call that a ion, that's what this is, to a dipole. IMF. All right, so we're going to do maybe one last topic. We'll see if we get there.